manufactured by one process. This is the experiment that I conducted. I used the specimen A and B for the same parameter for both material. So the stainless steel and my steel, I use the same parameter for wire feed rate and travel speed. For the specimen C and D, I use different parameter for my steel and stainless steel. But the constant for shielding gas and the shielding gas flow rate. So during the forging process, we construct the fixture to hold the specimen during the forging process. And then this is the hardness test. We tested on the stainless steel side, interlayer side, and the mild steel side. This is the tensile test. I use the miniature size for my tensile test because the constraint of our machine produce the bigger specimen. So we also build a fixture to hold the specimen during the tensile test. Because in the lab, we don't have the jig to hold the miniature tensile. And this is the results. For the dimension stability, I would say that there's no much different on the different and same parameter. So for forging process, we set the dial gauge to make it 5 mm, reduced from the actual thickness that we the actual group dimensions. And this is the CM image for the same parameters specimen. We can see that the A1 is the non-forging specimen. You can see that the oxide inclusions and the austenite and ferrite and the center line in the intersection, we don't have any defect there. But for the B image is for the forged specimen. So we can see some elongation at the stainless steel side. And this is for different parameter. Not so much different, but for the oxidizing spot is more likely to see on the mild steel side compared to stainless steel. And this is the EDX interlayer line. I just take the specimen B for the forged one. So we can see that after forging process, there's no diffusion on the elements in the mild steel or stainless steel side to the other side. You got ready? The element from the stainless steel side is not going to diffuse or moving to the mild steel side. But for the spot 1 and spot 2, we have the CR element. Means the CR element in stainless steel still on that interlayer line. Even though there's no diffusion, but it's still on that line, at the interlayer line. Okay, this is the micro hardness analysis. We can see that highest hardness is found in the B specimen, which is the forged with the same parameter. Even though that parameter is not really affect the dimensional, but it still affect the other hardness of that specimens. So we can see here the highest hardness is in the specimen B at the interlayer zone, while the lowest hardness is in the specimen C, which is the not same parameter but not forging. Okay, this is the tensile analysis. For the non-forged, we have 179 MVA, and the forged one is 284 MVA. But the elongation is still goes to the forged one because the maximum strain is only 1.658. But for this tensile, I do think that I need to repeat it again because the miniature tensile result is not, when we compare it to the normal specimen for tensile, it's not achieved that much. Some of the research make the get the tensile result as 700 something. But we use the miniature one. But we compare the forged and the non-forged, and we can see the effect from 179 to 284 after forged. Maybe because of we are using the small specimen, so the area to fool that in the tensile test is not much. So I think that's all from me. As a conclusion, the dimensional stability is not that much on that parameter setting, even same parameter or not same parameter. And the region examined as in bimetal structure, EDX, contain chromium at the interlining zone, even though there's no diffusion on the composition on both sides. And the this value is better on the forged specimen compared to the non-forged specimen. That's all from me. Thank you.
Okay, thank you, Dr. for the interesting presentation. Okay, we open the floor for Q&A. Anyone to ask any question? Yeah.
So one question, what are standard method used for tensile test?
Standard?
What are standard method used for a tensile test?
Method?
Yes, it is there is a standard method you follow, such as STM or whatever.
Yes, yes. We use AS we use ASTM ASTM 8, but E something, E8, I think. The small one.
A question.
Mine is not a question. I'm a little bit confused with the caption conclusions.
How many conclusions? Yeah. Oh, the term S.
Oh, okay.
Why that is S? So looks like just a single conclusion, but with S. Yeah. All right. Okay. My question is that, okay, we know that my steel and stainless steel has a different hardness. Okay, when we forge, what happened? Because we know that compared to my stainless steel, my steel is much lower in terms of hardness. So when we forge, if there is any effect to the material, for example, if we forge from the top, probably there is no deformation occur on the stainless steel itself, because my steel as compared to stainless steel is much softer. So probably when doing the forging, only my steel deform, not both materials.
supposed to be like that, but from that SEM image, we can see that the elongation is happened on the stainless steel side too. This one.
All right. Okay, thank you, Nadira, for the presentation. Okay, I think cannot enter the room. I think he using the different link. Tak keluar pun kat saya punya ni. Okay, without further ado, I would like to call next presenter, which is my FYP students, which is on features in production using 3D printing technology. Probably this project is very much related to Muntaka's project. Okay, please welcome. Setting the display. I don't know why. Yeah.
I show. Okay, thank you, Doctor. So, good afternoon to Dr. Aha, honorable guys, and also my fellow friends. I'm Ming Fang from School of Mechanical Engineering. We'd like to present my final year project with the title of Feature Reconstruction using 3D printing technology. So before we jump into the main topic for my presentation today, let's look at an example of the damaged product. So here are some real example damaged product with different problem feature in our real life. So actually, I could not find any journal directly related to the most common type of problem feature, especially for the polymer product. So I conducted a research of using journals discussing repair the damaged product and find various websites to find the common type of damage. So after I conducting the research, I found that the most common type of problem feature are generally classified in three types, which is flat, slanted, and wave surface problem feature. And the current problem that we face is that many people throw away the product with the minor damage, even though they're still functioning. And this goes against the idea of using resource wisely and being sustainable, leading to more waste. So the main issue holding this happen is because to reconstruct the damaged product can be expensive. So people will prefer to buy a new one instead of repairing it. And this will create a cycle of waste and harm the environment. So to solve this problem, a simple and affordable way to reconstruct the damaged product is required to reduce the waste and at the same time can be more environmentally friendly. So to get a cheap and efficient method to reconstruct the damaged product, 3D printing is the best choice among all. So the objective that I aim to achieve in this study is to reconstruct broken or damaged feature through trickle alteration, and the second is to evaluate the reconstructed feature for accuracy, structural integrity, and cohesion coherent to the original object. But for the presentation today, we will only focus to the first objective, and the second objective will act as my future work. So this comprehensive research initiative pioneered innovative 3D printing technology for precise reconstruction of problem feature. So this study is all about using 3D printing technology to reconstruct the damaged product, which means that I will use the 3D printer directly to print the damaged product part on the to print the problem feature part on the damaged product to reconstruct it and make it same as the original product. So subsequently, the experiment will emphasize on optimizing the object reconstruction process for precision and efficiency. Besides that, the project will also emphasize the testing and validating the proposed 3D printing reconstruction method involves evaluating the accuracy, structural integrity, and cohesion coherent to the original properties of the reconstructed object. So the testing and validating protocol will be implemented to make sure that the reconstruction of that has meet the higher standard of precision and reliability. And sorry. So here is the flowchart of methodology for the whole reconstruction process. So I will explain the crucial part on the flowchart. Since we want to reconstruct the problem feature, so the first thing is we need to have a damaged product, right? So in this study, I will create the damaged product by myself with the specific problem feature. And also I will using the SolidWorks software to create the problem feature part. And I will use this problem feature part to reconstruct the damaged product. After that, we need to save the damaged product and problem feature part as STL file and import both of them in the Ultimator Cura software. So in this Ultimator Cura software, there are two things that we need to do. The first thing is we need to assemble both damaged product and problem feature part together, which it will send with the original product method. After one thing is done to assemble both of them, the second thing that we need to do is we need to generate the G-code. So in this case, we have three types of G-code that we need to generate. The first one is the full assembly G-code. After that is the damaged product G-code, which is this one. And the third one is the program feature part G-code. So when we start to generate the G-code, we will move to the most important step for the whole reconstruction part, which is editing the G-code. So since I have mentioned before, I create the damaged product by myself. So the function of the G-code for damaged product is just use is to print the damaged product first. And the function of the full assembly G-code will use to compare with the program feature part. So here you can see the example of the G-code. So on the left side is the example of G-code for the full assembly, and the right side is the example of G-code for the program feature part. So before we convert both G-code, the first thing that we need to know is that the program feature part names. So in this case, since we know that the name of the program feature part, we name it as wave B1. So we can directly search the wave B1 in full assembly G-code by using Control F. So the result out is the first area of the program feature part in this G-code. So which means that at layer 244, the 3D printer will start to print the program feature part. So we know that at layer 244 is start. So let's also look back to the Z position before the printer start to print the program feature. So here we have shown that the Z position is Z49, right? Then we move to the feature part G-code. So for the original G-code for the program feature part, the first Z position will be Z0.2. But once we compare with the full assembly, we already know that before the 3D printer start to print the program feature part is Z49. So we directly change the Z0.2 to Z49, and the printer will read the G-code accordingly and start to print the program feature part and label 49.2. And since we already changed the Z position in this G-code, right? This one is the first Z position. So the other one we also need to change this by plus 0.2. So for example, the first one is 49.2, and the second one we need to plus 0.2. The second one will become 49.4. Third one will become 49.6, and change all of this until the last layer of the Z position.
Can I stop you first?
Oh yes.
Because the online dia nampak?
Okay, sorry. Okay, so till here is the crucial part for the whole reconstruction process. And let's move to the current progress and result that I get. As I mentioned in the literature review, right, the most common program feature are generally classified in three types. So in my study, I will also focus on the most common problem feature, which are the flat and slanted and also the wave surface problem feature. So for the flat surface problem feature, this is the damaged product, and this is the object that I done to reconstruct it. So from here, you can see I have successfully done to reconstruct the damaged product to the original project, original pattern, and this is the final result that I get. This one. So you can see, this is the sample of the original pattern, and the black color represent the damaged product with the flat surface problem feature, and the white color represent the problem feature that I use is to reconstruct this damaged object. So here you can see that after the reconstruction process, the damaged product already sent with the same original product, which means that 3D printing technology can successful to reconstruct this kind of problem feature. After that is the slanted surface problem feature. Then also we have the damaged product and problem feature part, and assembly both of them in the numerical catastrophe. So from here we got experiment 1, experiment 2 with using different editing G-code method. So the result of experiment 1 come out is not ideal due to the unsuccessful editing G-code method. Well, for the experiment 2, it's still the same method of editing the G-code. As I mentioned in the methodology part, which is editing the Z position in the problem feature part. So from here, you can see that the result of experiment 2 is better than the experiment 1. Because I didn't use 2 colors, so maybe you cannot clearly to see. But here you can see that this one. The white color is the damaged product with the slanted surface problem feature, while the red color is the problem reconstruction part. So from here you can see this also same with the sample of original product, and also the surface and interior of this reconstructed object is good. So means that the 3D printing can also to reconstruct this kind of problem feature. And the last one is our web surface problem feature. Then also assembly done and generate the G-code. But this type of problem feature is quite different compared to the flat and slanted, because you can see that the 3D printing, the noise of 3D printing will crash with the damaged product due to the layer problem. So to solve this problem, I try to separate the problem feature part into 3 parts respectively, and also assembly done and generate the G-code. But in this case, there are 5 types of G-code that we need to generate. The first one is the full assembly G-code. After that, the mass product G-code. After that, the program feature part G-code part 1, part 2, and part 3. So there are total 5 G-code that we need to generate. So we separate the reconstruction part, program feature part into 3. So the process of reconstructing the web program feature will also separate to the 3 types. For the process 1, we'll undergo to reconstruct the part 1, and process 2 will reconstruct part 2. Then the last process will try to reconstruct the part 3. And this is the result that I get, and this is the final result. And you can see the red color is the damaged product with the web program feature, and the white color is the reconstruction part, and also the surface and interior is good. So means that 3D printing can successful to reconstruct this program feature. So in conclusion, the findings of experiment provide evidence that it is possible to successfully reconstruct these 3 problem features using 3D printing technology. Although I didn't use any real damaged product in my experiment because I created the damaged product by myself, but the concept of using 3D printing technology to reconstruct the problem feature is verified. So means that we can directly use the 3D printer to bring the problem feature part on the damaged product to reconstruct it as with the original product. So after that, I will use the cohesion machine to evaluate the cohesion of the reconstruction object. This is as my future work, and also is the second objective that I aim to achieve. So that's all for me. Thank you.
Okay, Thank you for the very interesting session. Okay, anybody want to take drink? You can take from that other rooms before they take it back. All right. I open Q&A to the floor. Okay, Govind, first question. Is this a planning question or what?
No, no, no. I just want to clear my doubts.
Yeah.
Okay, so just now you show some of the examples for the business.
Oh, okay.
Minfa,
Ah.
just now you showed some of the pictures, right?
Ah.
Related to the common products.
Mm.
And I've seen most of the products are related to the household things. Okay, so since 3D printer, okay, there's a size limitation of that. Okay, so if it's size limitation, and one more thing, for example, if the certain parts, okay, they are cheap, they are even yes, and if some of the parts are broken, it's recommendable for them to go away and buy a new thing instead of giving to 3D printer because the people nowadays they don't have the knowledge to reconstruct. Okay, and if they give the things back to if they're gonna give to other 3D printing service to reconstruct back, it might be more expensive. So I want you to explain about that. How will you take this to market? Take this 3D printing to market? Yeah. I mean, how is this applicable to market? Because there's time limitation. And if you want to see 3D printing now, currently they got 3D print house and everything. But if you want to see small 3D printing, I don't think so. You can construct a big thing. Okay, so I want you to explain to me how this can applicable in the market because you say that most of the pictures there is mostly household. Okay, and then the second question is.
Okay, can I answer your first question first? Hello? 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 Can you hear my voice, right?
Yeah.
Actually, your question is maybe out of my project because the concept of my project is I want to prove that the concept of using 3D printing technology can be successful to reconstruct the problem feature. But your means that I want to bring this technology to the market, right? I think this one maybe we can cooperate with others industry and to introduce with them. Maybe this kind of technology is proved that by my project. Maybe for the need to improve because this is very basic one. So we can cooperate with the industry and it's maybe industry can also help us to tell with their customer and this will I think this maybe can help us to bring this technology to the market. This is my answer.
Okay, thank you, Tom. And my second question is, as you said that you didn't create your parts by yourself. I mean, you create the part by yourself.
Yeah.
The broken parts, right? Okay. So if the broken parts are made by the nature of someone broke it and everything, the surface would be even as that. It will be uneven,
Yes.
very uneven.
Yes.
Okay. So due to the maybe the accuracy of the 3D print and due to the material flow and due to the maybe the G-code alteration,
Yes.
how do I use that it is successful for that kind of features? Because for example, if it's straight even surface, it's just you just gonna increase the z-axis and then bring back the same. So based on my understanding of G-code, if it's rectangle and if you broke the upper part, you just have to increase the z-axis and then bring back the same thing on the top.
Yes.
That's my understanding of G-code. Okay, but if it's uneven, very uneven, like zigzag and everything, and how so are you that the G-code alteration can make a successful bonding between these two materials?
So I think this kind of question is same with what I have shown in the wave surface problem feature because there was also uneven, but it's a simple uneven example but same also because due to the limitation of the 3D printer, they only print it layer by layer. So if with the damaged product with the different layer, it will clash with the damaged products. As I showed in the previous slide, which is this one, the nozzle will clash with the damaged product. So if the damaged product is very uneven, very complete pattern, then I think the first maybe we can try the same concept with this, just separate the problem feature part If not, I think we can include the 3D scanner. 3D scanner to scan the damaged product. And also, we go to know the design of the original product. So after that, we can directly use the SolidWorks to draw the problem feature part first. After that, we can separate the problem feature part and try to generate the G code and print it up. Oh, so many questions.
Okay, for the separation of the survey, do you think that it's applicable? I mean, it's a the best way to reconstruct a product because you're gonna reconstruct back everything, so it's like a waste of material for me. So what's your comment about that?
For me, for now, my progress, I think this is the best method for me, because for the experiment one that I show, experiment one, like this one, this is a standard, it's a very simple program feature, right? But this also will crash, the 3D printer, the noise of 3D printer will also crash with the damaged product due to the layer problem also. And the editing, same with the, I already tried to many type of many pattern for the to edit the G code. And this experiment one, actually I using the, if you know how to use the Ultimate Kira software, you know that the problem feature part at this here, where for example, this is just an example. If I put the damage product at here, and I want to generate the G code for the program feature part, right? And I need to remove the damaged product. So if you know how to use the Kira software, you will know that if I didn't add any support in the setting, the Ultimate Kira software will automatically drop the program feature part down to the breakpoint, right? So I also try my best to generate the G code with the support. But the result count is not good. It's same with this one. It will crash also. So I think maybe 3D printer can help to reconstruct the program feature, but it have a limitation also, and it also can be reconstruct a limited program feature. That is my answer.
Okay, thank you for a very good question actually. Any other questions?
Hello everyone. Mine is not a question, but observation and contribution at the same time. First of all, let me comment the effort of the presenter. First one, the question came from the sorry, the name I forgot. Yeah, he made mention that how does this product extend to the market, which is very, very good question. So the way she responded, I also appreciated because she made mention what collaboration with the industries. So I believe with the help of the experts in this technology, this can be sent back to the market. Expected, as you mentioned, household. This important project should be extended even to the schools because the way I look at the models, it can be manipulated to produce learning resources. So in the long run, this kind of models, if properly produced, are related to the instructional materials that will assist our younger ones, more especially in primary schools, which they are more of using two-dimensional to support their learning process. So this also it will be go to the bookshops because there will be market for this whatever the need for the learning resources arise. I think it will be sellable. Thank you very much.
Okay, I didn't expect a question from you, Otaka, because this project is directly related to your project. Okay. Any other question? All right. Okay. Thank you, Papa, for the interesting presentation. Uh, I would like to call next one. Our next one is who is the next one? Mukri. Okay. Nanti dia present, mau tanya banyak. Okey, kejap ah. Dia salah. Okay, Mukri will present on optimization, and the main aim of the project is to optimize the deposition path of WAM. Okay, I think the project is not completed, but it's ongoing. So I would like to call Mukri to present his work. Dalam tak share sekejap. Nampak?
Okay, Assalamualaikum and good afternoon to everyone. So my name is Muhammad Mukri Syarif. This is my study for FIP research, which is the optimization of deposition paths of wire additive manufacturing. So this is my flow of the content, objective, and until the end. So the first objective is to construct a deeper programming for different path position and on profiles using KUKA robot. And the second objective is to observe the preliminary results on the effect of different deposition paths, shapes on time, dimensional accuracy, and also hardness. So this is my scope of work, which is we'll be using the KUKA robot. This the series of the robot KR10 R1420, which is located on Robotic Lab, School of Mechanical Engineering. So for the KUKA robot, I will create a G-code manually using according to the deposition path, and we create the after that we create the welding process. So this one is my literature review according to the journal. I have found several type of deposition paths, and I will search. I have searched the most suitable deposition paths for my studies, which is as we can see there are a lot raster, VZ, contour, but I need to find the most suitable for my research and according to the shape and also deposition paths. As we can see, I have this four F5 type of deposition paths that can be used for my research. And I have choose three type of deposition paths, which is raster, contour, parallel deposition pattern, and also spiral. So this I can claim that this is the most suitable type of deposition path to be used in three different type of shape, which is I will explain more in terms of shape, but this one is most suitable to be used to create the deposition paths on triangle, circular, and also rectangular. So this is a deposition type of three type of deposition. which is cover large areas and persistent layer by layer deposition. And this is the most easiest to and simple to program the code. And the surface finish, which is the profile, also good in terms of that. And also can be fixed into different type of shape and value shape, circle and also triangle. So this one is my methodology, starting from the literature review, experimental design, and maybe I will be using G-code. And from the programming, I can choose the writing speed and also the color. This one is my parameter. And after that, I will go to go no-go evaluation. If the optimization is not good enough, then I will recreate the G-code and choose the writing speed again. So for the go evaluation, we continue to the optimization process. So this one is my experimental design. I have come out to 9 experiments, 9 shapes, and also 9 different deposition pattern. So for the output is I want to find the deposition time, dimensional accuracy, and also the hardness test. So this one is just uh, output. The time duration for each layer, starting from after do the coding, and when the coding run, I will start to take the time taken. And for the hardness, usually we'll be using the Rockwell hardness test, and the dimensional accuracy, I will be using the micrometer screw gauge according to the plan deposition shape area. So this one is a type visualize what I have need to do, the type of shape and type of deposition patterns. There are 9 of it, and for the experiment one, I have done the 9 deposition plus, and this one is just a visual picture for you to see. And the second methodology is to create the G code according to the paths that I've chosen. For this one, as you can see, this triangle shape and parallel contour deposition pattern. And also this example of coding that I've done in the robotic lab using Kuka robot. So this one is how I have done to choose the type of parameter of the welding. So this one is robot velocity and also the current 80 ampere. The first try I've done is 0.598 meter per minute. So this is a welding parameter. And this picture is to show the gap between the difference of line deposition, the length of the deposition gap. So the first one is between this and this actually 0.5 centimeter. I have done with the same speed 0.598, and this one is 0.3. As we can see, the gap from the yellow part is gap about little gap, and this one is attached to each other. Okay, this one after that after the welding process, we will move to the milling. I will mill the outer layer and to see whether the deposition path is correct or not. If there is a gap, then I will go to no-go evaluation, and for the go, if the surface is have no gap between each other, then I will continue to evaluation on other. So for the optimization process, after the no-go phase, the goal is to achieve to save the time as soon as possible and also to achieve the higher accuracy of the patterns. So by increasing the time can make the bed harder and stronger. And by improving the material bond, its structure can cause a big problem too, because from the bed you can know that the tiny hole, if the bed bigger, there's tiny hole, so it can influence the structure itself. So by employing the leveraging method, I can systematically analyze the effect of different deposition paths on different deposition patterns and also deposited profile. So for the dimensional accuracy, it also refers to the degree of deeper precision and closeness. And also in this output, I also will be seeing on the most important geometric features such as length and width, and also angle of the final product. So this one is the result of my experiment one. This is before, this is after welded, and this one picture is one for after going through milling. So as we can see, most of the succeed pathway is linear contour parallel for the circle shape, rectangular, and also triangle. For other deposition paths, there are still a gap and will be improved in next experiment. For the three type of deposition that succeed, I will go through to the we go to the harness test and also optimization. This one is for the one of the effect of the parameter purging, which is the speed that I have used is the first one is 0.498 meter per minute. And after that, the experiment that I've used before that, the teacher that I used is 0.198 meter per minute. So this one is the gap and between the deposited pathway for the first bit and 80 ampere currents for this one. So this one is the result and the discussion deadline of 9 experiments, different control factors, and the original parameter that I have targeted for each of the uh, shape and pathway is rectangular 10 times 10 centimeter, and for the triangle 10 cm for the base and 8 cm for height, and circle is 10 centimeter diameter. So what I have got using the speed of 0.198 meter per minute, the derivation shows that the difference shows that the derivation parameter have the highest rectangular has the highest difference cluster, and the lowest is parallel. Parallel shows the lowest difference derivation parameter. So for the time taken for highest experiment is also cluster rectangular, and the best taken that I've getted is spiral and triangle. Spiral deposited, triangle shape. So for discussion, in order to achieve the best highest precision in welding parameter, I need to reconsider the welding currents and also the welding speed. And for the safety manner, I will choose the best thickness for the plate and to prevent the plate from melting. Okay, so conclusion. In the context of manufacturing, WAM to achieve the highest dimensional accuracy is to ensure the final product meets the specification and requirement outlined in the design. So for the upcoming progress, I will redo the deposition, I will redo the digicode program for non-go deposition pass, and after going through milling, and also I will move to the process on hardness test time taken and also dimension accuracy. And this one is just add on upcoming progress, which is I will use gap penetration to see whether the gap is between the deposition pass is good or not. Just to check of the bad gap between the deposition pass after grinded. So that's all for me. Thank you.
Okay. Okay, thank you, Mokri, for the presentation. Okay, actually, this project also related. Yeah, I mean, because for the FYP many projects, I usually do the groundwork, and then for the details, for master and PhD. That's why what we found just now, I try to limit the scope lah. Kalau nak cover the everything, I don't think we can finish it within 1 year lah. That's why I hope Muntaka will further detail the, the, the work in probably hardly or certain percent of what we found have done. But the approach, the methods, the way probably the same. We just apply and try to scope and limitations of their own works. Okay, any question before we to Mukri? Yeah.
So, Samsung, to create the G code, how did you configure the next position?
Actually, I will actually before I create the G code, I will draw manually the deposition line on the table, and for the plate, I will use the clamp and draw the pattern of the shape of the plate. So when I want to redo the G code, I can just refer to the previous shape of the drawn line, and the G code I will follow the path of the deposition path, and from there I can create code. No, understand. Okay, for the yes, you mean the continue the same path? No, that one is the reject one. So I will do the new wedding process.
For the single profile.
For the single profile,
Like for example, for the raster line, every single line we are creating a new code is a continuous.
oh, okay. For the raster, if the line is if continuous, then it is in single code program. If the no, I mean the in same code, no
Same file.
same file, but not in single line. But if the pattern required macam contoh example, if the line of the deposited profile not attached to each other, so I need to create new code for it every single layer. So if it requires 70 lines, 70 code.
Yeah. Okay, answer. Yeah, because this is a manual programming, and it's not the same to
Next.
I think they second the one, not after first line, first layer. It's already being programmed from the beginning. Is that they tak ada adjustment apa-apa lah. There is no adjustment in between that's what I understand.
Example, for the first code, for example, we are using 0.498. Then if I want to change to 0.198, I need to change every layer of the web parameter, every speed. But if I do the first code is 0.4, the most is 78. No, 78 coding. Layers 10.
Single stack.
Oh, it's 10. Yeah.
We don't want to make the complexity lah. That's why just how many layer. Solve the single layer first, then by extension layers. Yeah, go in.
Before and after those steps. Okay. Okay. I'd like to know. So the first one, after one row milling, the first one is the straight line counter, right? Second one is the square. The second one, the below, right? And then the third one is the pyramid, right? So I understand is if it's line counter and if it's square, at a straight line, it should be the same as the line counter, am I right? Only at the curve, there's a difference. It's square, okay? If it's straight line, it should be the same with the first one. You see, if it's line counter, you print one line and then you print the subsequent line. So if you refer to the square part, you can see the flow, the one line, second line, third line, fourth line. Am I right? If you see the square, 1, 2, 3, 4, there's 4 layers. Okay, so if you're using the same parameter, all this, may I know why? The first one is it's everything, the well-being, it's very good, and there's a joint between them. But the second one, with the same parameter, there's a defect and there's a gap between the lines, not the curve part, because the curve part, because you have to alter the G code and then the curve might be something else. But the straight line, supposedly with the same parameter, it should be joining. May I know why it's not joining?
Thank you, Bobby. So to answer your question, is for the reposition part, before I go to welding and coding process, I need to draw my reposition parts manually. So this might be the human error for me. So to become more accurate, I need to draw on the table itself. So I just draw on the plate. So as you understand, if I put the plate on the table, it might caused by the vibration of the machine itself. So some of the line is not accurate as I want to. If as you said before, so the line should be same as the previous one and the statement. So it might be the human error.
Okay, so you're using KUKA welding robot, right? If it's KUKA welding robot, correct me if I'm wrong, you'll be using point, right? Point system, right? Which means from one point to weld, right? Okay, so if it's point to point, may I know why that? I really don't understand why there's a big error in that. And if you say it's human error, I know how, because you are using G code, right? You're using G code, and you say that you're drawing on top of that. I believe that on top of that is just for your reference, but mainly it's about the G code. without, if you think that it's human error, and what's the function of the G code? If you are drawing it and you're saying that because of the drawing, is the Google value robot making mistakes? Because you're playing with the G code, am I right? You're playing with the G code. So G code is a point system from here to here, and then from here to here. So then you just set the, you just know the length, and you know how it moves. So so how I don't understand how does your drawing affect the thing, and if it's related to human error, how you want to overcome that problem? Because if it's not overcome until the end, you won't get the result. So how you want to overcome the human error? Thank you.
For the question pass, the Kuka robot itself is very accurate robot. So this is my assumption. I have drawn the 9 type of reposition pass on different type on different blade. So if I'm using the for example ruler,
I think the his question is that, okay, for example, this is a straight line. Straight line. Why, when we are using straight line, there is no gap between the band. It's about perfect welding. There's no but. Even though for you are using the same parameters, but for other reposition pass, why there is a gap between the band? Is it that?
Yes.
is because because my drawing is not accurate enough. So for the G-code of circle, for example, if I draw right here, and as you can see, this one is outer layer. This is caused by the overheated cooker. Then for the circular, an example, I plotted the line, plotted the point here, and point here. Somehow there must be some difference between here and here. So to increase the gap between the bed, I need to make the bed become bigger, and so to attach, sorry, problem, to attach the gap between the deposition pass and also the, understand?
Make it more confused. Okay, actually the answer is that, okay, before we go for programming, he just sketch using his hand. And then from there, he get the position manually. That's why you can see there is a inconsistent. That's why probably later, because this is the first try, probably later, you need to redraw back all those things using CAD, make it more consistent, and then rerun, reprogramming all the decode, and then put it back. Yeah, that's the answer. Yeah. Then the problem is that you have manual. You doing manual to draw this. Yeah, definitely will going not true, not system. All right. Okay. Yeah. Ada lagi soalan? Any other question? Ada other question? Zul, jangan nak soalan, macam nak tanya soalan? Alright, okay, thank you, Mukri. We go for the next presenter, the Joshua. Sorry.
Can I check first if it's out of place?
Okay, actually Joshua is not my development student. Actually, he's under the Indian Mozani. But he's doing my about similar project that we are doing on WOM. Probably, yeah, okay. Okay, nampak tak? Yeah. I don't know why we need to every time we need to reset the setting the display. Yeah. Okay, changes. Nampak? Okay.
I think. Okay.
Testing. Okay, so a very good afternoon to everyone here. And right now I will start my presentation. So I'm currently a final year student, and this year is my final year project. So the title is Optimization of forging process parameters on mechanical properties of additive manufactured products. And here is a description of it, which different forging process parameters were carried out on multiple specimens to find the optimal process parameters using Taguchi method. And my name is Joshua, right here, and we'll see the next slide. Okay, so this here is the introduction. So as we all know, wire additive manufacturing, uh, also known as WAM, is a metal additive manufacturing process that can produce metallic components for engineering and structural applications. And why it is so favorable in the industries nowadays, that is because it is cheaper compared to other additive manufacturing processes such as laser melting deposition, LMD, and also powder bed fusion, which is PBF. And it is also better in terms of material efficiency. Now, even though it is better, it may have some defects here and there. So that is where hot forging process comes in as like a finishing process to enhance the material. So hot forging process is a metal shaping process where the workpiece is shaped into a desired shape via hammering, upsetting, pressing, and so forth when the workpiece, after the workpiece is heated to a certain temperature. So in this case, for our project, we'll be using pressing. This year is the literature review. So I have done a few reviews on a few papers, and I have mainly referred to this one right here. So this one is a case study on the influence of hot press forming process parameters on mechanical properties of green composites using Taguchi experimental design. So as you can see right here, it's a bit blurry, but there are 5 process parameters in total, which are temperature, pressure, heating time, cooling system, and recrystallization soak time. And each process parameters are 5 here. There are 4 different levels. So in total, there are 20 set of process parameters. So what the paper here did is here different process parameters, and they have countless combinations, and in total they did 50 combinations. So with each combination, they are able to obtain a different set of data. So 5 process parameters, 4 set of levels for each process parameters, and as you can see that L15 orthogonal array experimental design was created, and using Taguchi method, an optimal set of process parameters will be selected for the best result. Now, for the problem statement, like I mentioned earlier, web may have some few defects if we do just do it normally without finishing processes. So one of the critical flaws from using web technology is that the deposited materials may face inherent weaknesses in terms of mechanical properties, such as internal pores inside the well beads. So this issue can be addressed by implementing a post-processing method such as hot forging process. However, further research and optimization is required to obtain the optimal process parameters to get the forged specimen with the best mechanical properties. And right here is the objective. So the objective for my project is to study the effect of forging process parameters on a material's mechanical properties and to optimize the forging process parameters on the mechanical properties of the additive manufactured profiles using Taguchi method. Right here is the scope of my project. So my project type is experimental, and this project will require experimental work and optimization to get the best result. And there are a few limitations for my project. And one of it is the non-homogeneous temperature between the punch and die specimen may affect the final outcome. So during press forming, the specimens will be placed on the punch and die, and it will press. However, because the temperature of the press and die won't be the same as the heated specimen, so that may have some sort of may affect the final outcome. And also the uncertainty of specimen's accurate temperature when it is undergoing the hot forging process. So the way I heat up the specimens is by placing them into a furnace. So there is maybe 1 meter distance between the furnace and the forging machine. So when I transfer it to the forging machine, the temperature may not be accurate with what I have previously set for the experiment. So this is a methodology. So I'll go through some literature review first, and then proceed to the process parameters where I keep the process parameters that I'll be using for the experiment, and then specimen preparation. So to start off the specimen preparation, we will go through wire arc additive manufacturing process. And after I have created those well-beat specimens, I'll go through hot forging process. And after the hot forging process, because in the end, I'll be cutting it to dot hole shaped specimens. So it cannot be very thick in order for the specimens to be working. So I'll go through milling process, and after milling process, let me go through cutting process to cut it to the whole shape specimens, and then undergo tensile test. Then after obtaining the results, optimization via Taguchi method and validation. So no means the result is not doesn't exactly fit the process parameters that I pick. So then I will need to repeat a few more specimens back here and start all over again. But if it is acceptable, then it will go to the end and continue. So this here is the process parameters that I use for the wire arc additive manufacturing to create the welded specimens. The wire feed rate is 5, travel speed is 50 millimeter per minute. The reason why I take such a slow travel speed is because I want my welded specimens to be as thick as possible in terms of width. That way, when I forge it, I can cut out the dot hole shaped specimen without any issue. And the voltage peak we pick is 4. And then for the optimization process, I have selected 3 process parameters, and each process parameters there are 3 levels. So for the forging temperature, it will be 500 degrees, 700 and 900 degrees Celsius. And thickness ratio is 0.95 to 0.81, 0.80 to 0.61, and 0.60 and below. So the reason why we did not pick thickness reduction for one of the process parameters is because if I do 2 meters thickness reduction or 3 millimeters thickness reduction, it may not be accurate because each specimen, even though we have fixed the process parameters for the wire arc previously, the specimens that come out may not be exactly the measurements that I want. So that way, we have used thickness ratio. So thickness ratio is final thickness over original thickness. And the last process parameter is cooling method, which is after the hot forging process. So the first one is air, the second one is water, and the third one is oil. And for oil, we have big engine oil. So with these three process parameters and three levels, I have made 9 experimental designs. So as you can see here, these are the experimental designs. So A1, B1, C1 will mean we will be using A1 is temperature, so it's 500 degrees Celsius, and B1 is thickness ratio, this one 0.95 to 0.81, and C1 will be air. So for this experiment, we'll be using that set of process parameters and so on. So that way we will have a few combinations that includes all the process parameters. And each experiment is conducted 3 times. So in total, 9 experiment number times 3, we will have 27 specimens in total. This here is the punch and die that we use for the experiment. So this kind of die is made of H3 steel. It is suitable for hot forging process, and because it is capable of withstanding high temperature. All right, and this here is a wet process. So as I said, mentioned earlier, we use 50 millimeter per minute for the travel speed. So that way we'll get very big well-being specimens, as you can see here. And after we have created the well-being specimens, there may be some unevenness on the specimens. As you can see here, there's like small bulging right here. So I have undergone use the grinding machine to grind it a bit to ensure that it is flat enough for the hot forging process parameter and hot forging process to take place. Now for the hot forging process, so as you can see here, 9 specimens were placed into the furnace, and this here is our technician setting up the forging machine. And this here is called a dial test indicator. So we use that to measure how much of a height that we want to compress the specimen. And this here is a photo of heated specimen before hot forging process. And after the hot forging process, we would let it cool down either by air, water, or engine oil. So for the air, it's not with any fan or anything. We just place it there and let it cool off on its own. Now for the milling process. So after the hot forging process, the specimen is still very thick that it is not suitable for making the dog bone shape for tensile testing. That's why milling process takes place. And what I said is for the final thickness of each specimen, it is supposed to be 4 millimeter. There will be some inaccuracy, so each specimen will be 4.00 plus minus 0.30 millimeters after it is milled, as you can see right there. And then lastly is the cutting process. So after it is milled, it goes through the cutting process. So for the cutting process, we have used lazy water jet cutting. Then it will basically make this dog bone shape specimen out for us to undergo our tensile testing. And right here is the tensile test. So each experimental design, there will be 3 repeated specimens. So as you can see, 3. So before undergoing the tensile test, I mark each specimen with their number. So in order to not mix it up later when I put it back in the container. So for the rate at which the this right here, by the way, is a UTM, which is a universal testing machine. So before going through the tensile test machine, I will need to set the stretching rate of the machine. So the stretching rate of the machine I think is 1 millimeter per minute. And right here you can see it's very small. The UTM machine basically grips together the specimen, and then it will slowly stretches until it eventually necks and breaks right here in this picture. For the results, so I have not done the optimization process yet, but I have obtained the results after tensor testing. So based on what I have done based on what I have analyzed from the results, high temperature use will increase the ductility of the specimens, and high temperature will also decrease the ultimate tensile strength. This one is a bit inaccurate because each of these are combined with other process parameters. So this one right here, okay, so it says A1, A2, and A3. So A1 is 500 degrees Celsius, A2 700, and A3 being 900 degrees Celsius. So right here, higher temperature will decrease the higher temperature use will increase the ductility. So as you can see here, A3 is 900 degrees Celsius used on the specimen. So that means it has increased the ductility. As you can see for the strain, this is a stress strain curve. The strain has increased here until here, where it eventually breaks. Then A1 being 500 degrees Celsius, it breaks around here. So it has proven that a higher temperature used on hot forging process on the specimen would eventually increase the ductility. And the next being B1, B2, B3. B1 is these are thickness ratio. So higher thickness ratio will decrease the ductility, which will lead to a decrease in tensile strength. So B1 being the lowest thickness ratio, B2 being moderate, and B3 being the highest thickness ratio. So as I said, highest thickness ratio will decrease the ductility. As you can see here, B3, the specimen will neck and break at around 0.3 right here. And B2, it will break around 0.35, and B1 being the lowest thickness ratio, it break pretty far away at 0.4. Now for conclusion, the effect of different forging process parameters on a material's mechanical properties were studied and analyzed. And the optimization of forging process parameters on the mechanical properties of additive manufactured profiles using Taguchi method will be carried out as a future work later on before I finish the project. And that's all from me. Thank you.
Okay, thank you, Joshua, for the presentation. Is there any question from the floor? Any question? Yeah, okay, as well. Okay, what you have found just now, they say that increasing temperature will increase the ductility, and increasing temperature will decreasing the gas. Is it in agreement with the theory? If you look back into the strength and strain curve, yeah, is it in agreement with the theory or not?
Sort of, because this, right, even though we use different temperatures, but it is still each of these specimens still undergo, like, even though this one use A3 uses 900 degrees Celsius, it is one of the combinations. So it may have used like oil as the cooling medium or another thickness ratio. So that has affected it a bit as well. So it's a bit inaccurate because it has already combined with other combinations as well.
Okay, when we relate with the thickness ratio, right? When we increase the thickness ratio, most likely the hardness will be increased as well. Right? Did you take into consideration that? Did you measure any hardness?
Not yet, but they can be considered, as I do have the specimens still intact, so I can still undergo hardness test to get the results later on.
Yeah, but by theory, if we increase the thickness ratio, means that more compression, more deformation, means that will increase the hardness, right?
Yes.
Increase the hardness will reduce the ductility or increase the ductility.
I think increase. I think the use.
it will increase hardness, more brittle. Right, more brittle, less ductility. Yeah.
Yeah. So correct.
Okay. Alright. Okay, that's all. Thank you from me.
Thank you, Doctor.
And next, you're fine. Okay, thank you. Just one.
Doctor.
Sebab apa dia kena tiap kali nak ni dia kena ubah setting. Still. Okay.
Hi.
Oh.
Okay, Assalamualaikum warahmatullahi wabarakatuh and good afternoon everyone. My name is Muhammad Irfan bin Lamal Barit, and for my final year project, I will be focusing on the optimization of the laser welding process parameters on the aluminium to the mild steel blanks. So this is the content for my presentation today, which is consists of objective, background, literature review, methodology, welding parameter, and the conclusion for my progress. So for the objective, I want to achieve for this final project is to analyze the most significant parameters to the weld joint by observing the weld joint strength, which I will use a laser welding machine, and will be determined using the WT method and ANOVA. The analysis that I will use is by tensile test tensile testing. So next, so this is for the background of my FYP. This is related to the welding process, which is a fabrication process that involves the joining materials, which is the fusion welding. And I will try to join the material with similar materials, which is aluminum to the steel. And in order to get the optimum welding parameter for the laser welding machine I will use Taguchi method and ANOVA. So this is the first literature review that I've found from the research. The first is the laser welding. So the laser welding, the source of the laser welding is from the laser beam. The laser beam can be consisted of carbon dioxide, solid state laser, or the fiber laser. And for the laser welding, the process that you it is the process that use a concentrated heat source in the form of the laser to melt the materials which fuse together as they cool down. So as you can see from the diagram, from the graph, it will show that the high energy welding, which is laser welding, will give a more advantage compared to the gas welding and the arc welding, which is it will give the high energy density, high welding speed, high precision, dependability, high productivity, and quick cycle time. So the second research, the subtopic that I want to present is about the visual welding. Visual welding is a type of welding process that involves the melt and joining two or more materials to form a cohesive bond. Then the visual welding will be involve a heat supplied to the material to the point where the melt and fuse together, creating a unified joint upon solidification. So for the manufacturing process, as if to join the process of joining, it has consists of three methods, which is welding, adhesive bonding, and mechanical fastening. So for my final year project, I will use the laser welding. So we will be focusing on the fusion welding. So next. So this is the basic types of joints in the fusion welding. But for my final year project, I will use a butt joint. So the third one is the similar material welding. The similar metal welding, the process of welding materials with the different alloys through welding, which means that the materials we will join it with the post will have a different nature, such as from the physical properties and chemical properties. So the laser welding of the similar, this is the research that I found from the articles, which is from the MFRL and GDE, which is they're from the Department of Mechanical, Nuclear and Production Engineering from the University of Pisa. So the research is focusing on the laser beam welding of the similar ferritic and magnetic stainless steel, which is supposed to have the different nature of the metal. So the goals of this research is to prevent the microcrack formation during laser welding by adhering pre and post weld heat treatments. So on this project, so we will focusing on the tensile strength test. So testing is mean that the descriptive test process that provides information about the tensile strength, yield strength, and ability of the metallic material. It measures the force required to break a composite or plastic specimen and the extent to which the specimen stretches or elongates to that breaking point. So for the form of the presentation, we will follow the accordance ISO SO5274, SO5275, STMD 608, STMD 30369, and STMC 297. And we show the graph here is the stress versus strain curve. So for the data analysis, we will use for Taguchi method and ANOVA. The Taguchi method, this technique will find the best parameter setting, while ANOVA adds in ranking the parameters according to its important. And if a thorough graph of the most important variables is provided by this integration. And for ANOVA, it's employed to analyze the variance in the response variable and determine whether the differences observed in the experimental results are statistically significant. The primary effect of each component and the iterations between them can be found using ANOVA. So we will go through the methodology. This is my project flow of my final year project. So we will start with the first semester. I will finish my research about this project, about all the literature review that I mentioned before. And then for the second sem, I will start to find the sample and test it with the laser welding machine. However, my progress now is pending since the laser welding machine is under maintenance. So inshallah in first week or second week after this, I will start the welding process since the technician already informed the quotation about that. So this is the material and equipment that we will involve, and this which is I will use the mild steel and aluminum, and this is the laser welding machine with model HW2000, and then we have a laser heat that will be involved with the mild steel wire feeder. So this is the specification of the machine that I get from the seller of the machine itself, because I contact him by email. So the laser type that we use here is the CW, which means continuous wave. Because the type of laser we have two. We have a continuous wave and pulse wave. The continuous wave will be emits the laser in the continuous without any gap. Meanwhile, for the pulse, it will have gap each emit of the laser. So the power of the machine is maximum of 2000 watts. And that's another thing, the welding speed is the maximum that we can go is 120 millimeter per second. So for the deposition cost, for my experiment is only use a straight line because I just want to weld the two here with only in the middle, just weld it by using butt joint. So this is the parameters that I get from the articles. This is just for the suggestion because I didn't do the sample yet. So I just get this is the parameter for the my steel if you're using a laser welding. So for my sample, I will use a 1.5 millimeter because the machine only have a maximum thickness can go until 3 mm. So the technician advised me to use below than 2 mm. So for my sample, I will use for my steel and aluminum, I will use for 1.5 millimeter. And afterward, this is for aluminum. So this is the planning for my data analysis before I start the welding. So the dimension for the sample is 120 times 100 millimeter per sample. So so for the conclusion, based on the comprehensive literature review that I found that laser welding offers a method for joint filler materials like steel and aluminum. The technique already been experimented as been recorded in the articles and journals. The parameters that I choose for the experiments is the laser power, laser focus, and the speed. Yeah, because the laser welding machine can be adjusted for its speed and focus and the power of the laser itself. So the significant parameters of the laser welding process will be analyzed afterward by using Taguchi method and ANOVA. The ANOVA will help identify the important variables influencing the welding process. Meanwhile, for Taguchi method provides an organized way to conduct experiments by methodically experimenting with different combinations of parameters. So that's all from me. Thank you.
Okay, for your information, Irfan has not run any experiment yet. He just go through the literature review. And unfortunately, when he want to start the experiment, mission broken. So I don't know how you want to solve that. You need to discuss that with his supervisor. All right, any question from the comprehensive literature review by Irfan just now? Okay, no question, thank you. All right, next we go to Govi. Gonna stop. Apa kena tiap-tiap kali ni lah kan? Okay, please, Obi.
Okay, thank you, Dr. Baha. A very good evening to my supervisor, Dr. Baha, and my fellow friends today. My name is Dr. Krishnan Alexander, and the register number is 152908. Going to present about the design and fabrication of rotating axis for pipe construction using wire additive manufacturing. So the table of content for my presentation today is the first from the introduction, then project background, model statement, moving towards objective, literature review, methodology, results and discussions, conclusion, and future goals. For the introduction part, additive manufacturing, also known as 3D printing, is a process that utilizing computer control process on producing products by depositing material layer by layer based on the program command. So for one, they are using electric arc, and moving towards the classification of AM, if we looking towards the direct energy deposition, there's three type of welding, wire is electron beam freedom fabrication, wire laser additive manufacturing, and wire arc additive manufacturing. So advantages of one, it's a high deposition rate and material, high material utilization, low capital and material cost, design flexibility, and some industry use this technique for repairing and refurbishment. So my project background is the goal of the project is to weld a long cylindrical pipe on the x-axis using rotating gauge. The helical shape approach will be utilized to form the pipe due to high dependence between jig and 3D welding machine. The initiation of the project occurred due to Z-axis limitation to deposit layer by layer to construct a decent length of pipe. Thus, a new method need to be figured out and improve the existing 3D welding machine. There's three main problem statement.
Okay, we open back. Nampak dalam? Kat sini ada? Gerak? Okay. Okay, see.
There's three problem statement in this project, which is the traditional pipe manufacturing extrusion process faced significant challenges in producing non-uniform thickness and profile pipes. Then in WAM, the welding process are limited to three special access based on our current welding machine. And the special access movement in the current WAM machines is constrained to a limited number of layers, restricting the production of pipes with intricate design and varying thickness. So the objective of the study is to design and fabricate a rotational axis module, then to develop a programming using G code for pipe fabrication. The next one is to optimize the welding parameters in obtaining good pipe quality. So currently I'm focusing on three objectives together to form the best pipe fabrication using the rotational axis model. So there are some literature review that I found in the journal. So the first one is that there are 6+2 welding robot axis, 3-axis CNC welding machines and 5-axis welding robot. Then related to 4-axis, there's CNC welding machines respect to Z-axis rotation only. And moving towards the machine parameters and optimizations, the intricate interplay between parameters such as layer thickness, travel speed, arc voltage, and wire feed rate hold the key to achieve superior quality of the additive manufactured components. So these are the parameters that we have to focus in getting the good manufactured part, additive manufactured part. And then the optimal welding parameters for weld surfacing of thin layered walls will obtain at a welding current of 59 ampere, welding voltage of 8.8, welding speed of 5 mm per second, where the linear heat input was 103.8 kilojoule per meter, and this is based on research papers. So moving towards the pipe construction using WAM, the conventional approach involves depositing metal layer by layer, but it's on the Z-axis only for current approach. And then there's a effect, which means there's an overflow of the the metal molten, and then due to uneven thickness and then structural defects, so there's a limitations in that. So the methodology of this project is, I'm going to start with some parametric studies on the designing and on the optimization of the parameters, get some of the best parameters for me to have a head start. And then going to do a sprocket designing to synchronize the axis module and my welding machine. And then fabrication of the sprocket, moving to assembly and the synchronizations, pipe construction, and the end of this testing. So for parametric studies, my objective is just to get a rough idea on the best parameters for me to weld a pipe, and then for me to have a guide to design a sprocket. So these two things that I've studied as a head start for my project. And then for sprocket designing, I have calculated some of the gear ratios and the best gear ratios for me to achieve a good pipe quality. And then I've done the CAD modeling using SolidWorks software. Okay, so this is the fabrication of sprocket. I've drawn the sprocket from using SolidWorks and then transferred to the 3D printer. And then using the Ultimaker Cura software, I fabricated the part, and some of the burrs I removed it through filing. Okay, so to connect the rotating axis module with the wire anti-manufacturing machine, I use sprocket, this fabricated sprocket, and then I have cylindrical jig, which I'll be explaining later what is this for, and then some chains here. Okay, so this is the way I assemble and disassemble the chains using the chain cutter. Okay, so this is my overview of my rotating axis module. This is through CAD model. I didn't pick the real positive axis module. So from here you can see there's a support, base support, the bearings for to allow the rotations, and then cylindrical rod is where to act as a support for our pipe fabrications, and then the screws to make it stronger, the sprocket, and then the chain, and then the chuck and chuck jaw. So the chuck jaw is to hold the piece itself. Okay, so I am using the SolidWorks itself. I have rendered my CAD drawing towards our machine. So this is the basic concept. The one of the sprocket will be attached to our rotating axis module, and another sprocket will be attached to the machines to allow synchronizations and to allow good pipe fabrication. Okay, so my project haven't completed, but we have done some file sections on the pipe fabrications. So the coordination between the rotating axis module and the 3D welding machines was evaluated at a reduced speed, okay, to see the synchronization between these machines. And then we have done some experiment procedure, and I have attached some videos over there. Then two main parameters are being the primary focus during the process, which are the touch traveling speed and metal deposition rate. Okay, let's watch some videos. If you guys can see from the video that if you guys can see there's a chain movement over here, and it's due to the rotation of the x-axis of the torch, and then connected to the sprocket attached to the workpiece module, and then due to that, our chuck is also rotated. At the same time, the cylindrical rod is rotated. So this is the basic concept. This is the basic synchronization made using the sprocket chain mechanism. Okay, I will play the second video. So you guys can see that this is the welding process at reduced speed that I've attached as a short video. Okay, because it was hot at that moment. So this is the basic. So when it's rotated and when the torch is traveling x-axis at a certain speed, we can get a nice helical shaped pipe using one. Okay, so this is the trial session that I've made with some parameters I've told you guys before. That I have to make it constant the deposition rate to 1 knob, and then I have made it to 2 knob. Okay, the 2 knob results haven't completed, so I didn't attach in the slide. So this is the first knob. First knob means it's around 36.6 mm per second deposition rate with a varying travel speed of 7 mm per minute, 6 for B. So I have labeling from A, B, C, D, E, F. So based on this, you guys can refer to the table there, the different parameters, and we can see that good bonding between two weld bit in E and F, which is around 5 to 5.5 mm per second, but this is not the conclusion. It will undergo more trial sections to get the best bonding between the two weld bit. In conclusion, the progress made in utilizing rotating axis module for pipe fabrication using WARM represents significant advancement in additive manufacturing technology, promising enhanced metal fabrication process. The synchronization is achieved between the rotating axis module and 3D welding machines through the sprocket chain mechanism demonstrate a mechanical solution that operates autonomously without the need for electrical intervention. This innovative approach not only streamlines the manufacturing process, but also contributes to cost savings by minimizing the reliance on electrical components. And then the extensive testing of numerous parameters in the fabrication process aimed at producing a high quality pipe with minimal defects has yielded valuable insights and improvement. So next, my future works will be explore the additional parameters until achieving the closest approximation to a well-formed helical sheet pipe, and consider utilizing sprockets if necessary for redesigning, including adjustment of gear ratios. And following this, the fabricated pipe will undergo die parameter testing to ensure its quality and detect any potential flaws or defects. Thank you.
Okay, thank you, Gobi, for the interesting presentation. Actually, our intention is that we will to construct a 3D plus 1, 3 plus 1D for the welding, something like that. That's our intention lah. That you know whether it's live or not. Okay, any question from the floor? Yeah. Any question? Okay, you said that you want to change the gear ratio. How you want to do that?
Actually, now for current ratios, I make it both same 12 to 12, which is 1-to-1 ratios. And because of the load, because when we deposit the metal layer by layer on the jig, on the rotating axis module, we will increase the load. So due to that, we need more force, more torque. So due to that, I haven't done the calculations for that particular load, but I will be doing it in case we need it for that the gear ratios to pull, I mean to rotate the axis model even stronger.
No, my question is how you want to change the gear ratio?
How am I going to change the gear ratios? By designing a new sprocket.
You want to use design sprocket, means that every gear ratio changes requires new design of sprocket. After that,
No, because my objective is to create a pipe for that particular rotating axis model. So I want to create the best pipe, so I have to create the sprocket. So and the sprocket is made up of 3D pins and I am very sure it's cheap compared to machining using metal to fabricate the sprocket. So it's replaceable if we want to.
it's not an issue of metal or plastic. It's a matter of you need time to redesign. Every time you change the gear ratio, you try to you need to redesign the sprocket, spread it out, and test it. Is it going to be repeating works?
Actually, to design a sprocket, it takes very less time, and then to print out also takes very less time. It can be finished within less than 30 minutes. So, in my opinion, that changing the sprocket only is not the major issues in this particular project.
Is practical
Uh,
in design in a real application? Is it practical?
in real applications, even we using many machines, many conventional machines, we are changing the tool and everything based on the needs. So I'm very sure that we are not changing the whole machines. We are changing the small sprocket, and the sprocket is removable. It can be assembled and disassembled. So I'm very sure that only changing the sprocket, we cannot fix one for everything. Certain thing we have to change for many design products. As like conventional machine, we have to change the tools, we have to change the tool holder or something. So yes, I'm very sure that it's applicable.
Is practical? My question is practical or not? Applicable? Yes, applicable.
Yes, it's for me it's practical because we cannot make one for all.
Okay. Okay. What about bicycle? Yeah, there are many types of size of sprocket.
Yes, so we change our sprocket based on the thing that we want to fabricate.
Yeah, we can do it just by changing the sprocket. We don't have to want to change the ratio, we need to stop, we need to design, we need to print, we need to reassemble that. That's easy. Assuming it's good. That's my question. Is it practical or not?
For me, it's practical.
For me, no. It's not practical because is it good in terms of design? Every time we change, you need to redo it back and redesign, refabricate. Is it good practice?
For this project, no, but for real world applications, yes.
You learn about lead, kan? Is it lead?
Definitely no.
That's the answer. Okay, thank you, Govi. Okay, our last presenter, Atir.
Yes, doctor.
Yeah. You can start, share your slide and your presentation once you are ready. Atir, you there?
Yes, doctor. Just I
Yeah.
have just a minute, please.
Okay, wait. Okay, just a brief introduction about Atil. Atil is a PhD student. About a year ago, he's a jet fighter pilot in Iraq. He's a Air Force officer in Iraq. So he's doing on his research is on composite, doing on simulation to study on the composite performance. Yeah. Okay, we
Doctor,
can start
it's not
attending
good.
your idea.
Yes, Assalamu alaikum wa rahmatullah. I'm Athir Najim from Iraq. Thank you, Doctor, to give me this opportunity to explain my presentation. I really appreciate it. I know I'm the last one, and maybe all the people there it's exhausted. I try to just like explain fast. Thank you. Did you hear me, Doctor?
What?
Hello?
Yeah, what is it?
Okay.
We have about 15 minutes.
Okay. It's my clear. The loud is
Yeah,
clear.
very clear, very clear.
Okay. Okay. My title it's whole integrity as assignment of carbon fiber reinforcement polymer composite panel using finite element method. I will illustrate in this presentation just like a highlight is introduction and literature review, problem statement and research objective, and the methodology, and final is reference what I'm using. The sorry,
Next, slideshow, please.
it's not sure.
Slideshow, so that we can see a bigger slide.
I'm sorry.
Just
I have a problem with the
put your
internet. I
button
think.
at the bottom on the right bottom before
Yeah,
the
sir.
zoom.
But sir, I have. I think.
Press the slideshow at bottom because you can see a bigger size of the slide. Now it is in yeah, okay, that's
Is that happen now?
that's
Okay. It's you know all the people we have like the composite material is very important with the especially with the aircraft and the aerospace industry because we have like many facilities. For example, I will talk about like for the commercial aircraft. Now the Boeing and Airbus. It's very important about the composite materials because you have like a high strength to weight ratio. For example, carbon fiber reinforcements are one of the main categories of composite materials in extensively used in aerospace application. More specifically, lightweight design has gained importance in the aerospace industry. Composite materials, for example, make about 30% of the outside surface area of the Boeing 737 and reach to 50% of the primary structure of the Boeing 787. It's very high percentage, and it's very important to study these materials and know the mechanical properties. I illustrate in this some people he worked with the carbon fiber before me. For example, it's in 2018, Mr. Komar he's studied the analysis of the wing and aircraft using carbon fiber reinforcement polymer okay, and the glass fiber reinforcement polymer, and compare with the aluminum. And he study, and after he will compare, he found the carbon fiber it's the better, and he's save money, because fuel consumption is very important with the aerospace industry. Here it's in the, for example, in 2022, Mr. Tan it's a study the systematic drilling damage, and what's happened, and when he's like make a drilling process, and he found the enhanced delamination mainly caused by the incomplete fiber cut off the top layer and the secondary cut edge, and using support plate. This from this study, he will focus about the support plate, and in my study I will already use the support plate, and I will show previously what's the benefit of this support plate. I will like modify this like a table, and in the future I will make some key finding. I will compare the parameter from each one from these people before me, and I will compare with my study, inshallah. Problem statement. The fatigue behavior of composite materials under various load and environmental factor. Study and know the behavior of composite materials under various load condition, okay, and design and optimize of lightweight structure with the enhanced reliable and safety. The study may be involve various techniques such as testing different composite materials, examine the effect of the hole size, and the feed rate and cutting speed. This parameter I will study and show what's the effect of each from these parameter, and know the stress distribution around the hole. Objective of my research is to development methodology and using it to evaluate the whole integrity of carbon fiber reinforcement polymer composite panel, and analyze the stress distribution, strain construction, and failure mechanism in the carbon fiber reinforcement polymer panel with hole under various load condition, tensile and compression and bending and extra, to investigate the effect of different hole configuration such as diameter, feed rate, and cutting speed on the structure integrity and mechanical behavior of carbon fiber reinforcement panel. Here I will explain the methodology. You know, the finite element, it's very important to especially in the engineering, to make him like estimate what's going on before he will be in the experimental work. I will study the use abacus, the finite element abacus, to mechanical parameter involving the drill hole feed, and like I say, I will use different speed, spindle speed and feed rate, and different diameter. Geometry, laminated carbon fiber reinforcement plate with overall dimension. I will take my dimension, it's like a 100 millimeter and 50 millimeter, with the highest or thickness 4 millimeter, with modeling and individual thickness. Each layer will be like a 0.25 millimeter, as known in the figure 1. Carbon fiber, like like I say, it's a composite sheet. Will like I will divide this like each layer is like I say 0.25. The total will be used like 60 layer. Okay, the orientation I will use like packing blades. Uh, like I say, many people who use this packing blade, and we have it's a lot of benefit for the packing blade. For example, it's a prevent of delamination, improve hole quality, reduce fiber pullout. It's a lot of benefit from this pack plate. But I see many people use just like one pack plate from under the the materials. I will make two. One it's under and one it's upper the materials. And I will make the first layer and the last layer is like a woven orientation, and during and 14 layer is like a 0 and 90-degree orientation. Three different dimension bit we'll use in this study: 6 millimeter and 10 millimeter and 12 millimeter mesh. The mesh using in finite element analysis was optimized through extensive mesh convergence to the modeling mesh. Focus on finite element around the opening and region of interest. Ensure mesh quality and element type suitable. Boundary condition, the drilling feed and spindle rotation were applied at like a reference point, center of the blade, and will like I will make the drilling just rotation about X direction and fix it in the and freedom about X and Y direction. Drilling parameter setup will use like I will illustrate in this table. I will use the feed rate, different three feed rate, like 005, 01 and 015. The drilling speed I will use like 600 RPM and 1000 RPM and 1400 RPM. And hole diameter 6 and 10 and 12. After I will finish the study, I will post result extract result for each simulation, stress distribution around the hole, displacement of the panel, damage initial and progress, failure mode, delamination and fiber. All these I will study during this study. Residual stress of the panel and after drilling, and plot contrast of stress, displacement and damage create quantity effect of different parameter, and I will compare all these parameter and result from different simulation. Last thing I will like I say, I will use many reference, and I will try to make a schedule like our table to compare what each one what he use and what I use, and inshallah after that I will be found the better parameter. Thank you for your time, and sorry about the problem from the beginning.
Okay, thank you, Akil, for the presentation. Okay, any question from the floor? Okay, my question is that are you going to study the whole integrity or the drilling process of a whole?
Excuse me, doctor, just your sound is not allowed. Please, can you repeat?
Okay, can I know whether you are going to study the whole integrity
Yes.
or the drilling process of the whole?
No, you know, doctor, it's the to know the integrity and the accuracy of the whole. I have to like study a different parameter, okay, and know the effect of each parameter to the integrity. For example, the spindle speed. When I increase like more than like a limitation, I will make a damage to the whole. That means I will affect the integrity of the whole.
No, in order to do to study the integrity, I don't think you need that parameter. Only you need is the strength of the whole, right? The properties of the whole, the strength.
Yeah.
That's the thing. But why we need to do the drilling process? Because you can get it all the properties from the literature.
Yeah, what I will work with it. I how can I like get the integrity or be sure it's that the holes it's like it's without any damage, without any crack, for example, delamination, pull out. It's that's how can I know exactly?
Yeah, it's true. But you can get that from the literature. Why you are wasting your time to remodel it? Why you didn't you need that? Because your main intention or main objective is to study the whole integrity. Or you didn't need that. You didn't have to start with the drilling. That's just wasting of your time. You can get all the information, the properties of the whole, properties of the damage of or the bearing strength of the whole itself. You can get from the literature. There are a lot.
Okay, doctor.
Yeah. Because I afraid that because to start to model the whole the drilling process is complicated, and that's not our main intention or main objective.
Copy, doctor.
Yeah. All right. Okay. Thank you, Ater, for the presentation. All right.
Thank you,
I
doctor,
think
for your time.
yeah. Okay. That's the end of presentation for the seminar today. I hope everybody get the point so that we can improve in the future. And most importantly, we can share our findings, share our progress, and then probably from there we can get some feedback from the audience lah. Not now, probably later. Probably if somebody will contact you or contact me, give some suggestion to comment on your work and so on. Probably, hopefully, you can get that. And then that's all. I think. Thank you everybody for the time. The second time attending here, Dr. Alimi, our alumni is still remain here until the end. So thank you for coming and spend your time with the seminar. And hopefully we can collaborate someday we can collaborate in anything in research and so on. Because I don't know, KTM whether their staff is required to publish paper or not. Dr. Azam is now keep their boss keep pressuring them to start to publish a paper. So that no choice. We need to collaborate with universities so that we can do some research and publish papers. All right, with that, I think that's all for me. Thank you again for your time. Thank you again for attending the seminar. Hopefully everybody can benefit. Muhammad Nazri is my housemate actually dulu at Toronto. He's one of the committed attendees lah for our programs, from I think our webinar and so on. Keep attending and joining the event. Alright, thank you again. With that, I think that's all. Thank you. Assalamualaikum warahmatullahi wabarakatuh.